Imagine having two, like, absolutely flawless maps to navigate your life.
Okay.
And they're both incredibly detailed, right? Like, in their own specific areas, they are completely unassailable, empirically robust.
Right, they were perfectly.
Exactly. But there is a massive, massive catch. They use completely different, fundamentally incompatible coordinate systems.
Oh, yeah, that's a problem.
Right. You try to overlay them to figure out exactly where you are, and instead of getting clarity, the coordinates just contradict each other. The landmarks blur, and you find yourself mathematically and conceptually completely lost.
It's a deeply disorienting reality to grapple with, for sure. You hold one absolute truth in your left hand and another absolute truth in your right hand,
Yeah.
yet they just aggressively reject one another the moment they are forced into the same space.
And that dual map paradox is exactly where modern physics is stuck today.
So, welcome to today's deep dive. We are exploring a fascinating attempt to finally draw a bridge between those two maps.
It's a really exciting one, too. It is. We're looking at a highly ambitious paper. It's titled The Planck-Chai Hyperexponential Correction Model to the General Theory of Relativity for Quantum Fields. And, what immediately stands out here is that the author of this source material, Julio Chai, is approaching this from a uniquely interdisciplinary angle.
He really is. I mean, Chai is not your traditional theoretical physicist operating out of some, isolated academic silo.
Right.
He is a Bolivian economic and systems engineer. He's a CEO, a polyglot who speaks 5 languages, I believe.
Wow, 5.
Yeah, and an aggressive lifelong learner. And that systems engineering background is crucial here.
How so?
Well, because systems engineers are uniquely trained to look at boundary conditions, they look at complex interactions, and importantly, structural failures.
Oh, I see. They look at what happens when a system just flat out crashes.
Precisely.
And Chai is stepping right up to the most famous system crash in the history of science.
He is. The mission of our deep dive today is to explore how Chai proposes to finally reconcile general relativity, which is our predictive map for the macro universe, right? The physics of stars and galaxies.
Yeah, the really big stuff.
Exactly. Reconciling that with quantum mechanics, which is the probabilistic map that governs the microscopic subatomic realm.
Right, and we all know the standard problem here. General relativity works beautifully for the cosmos, but spits out these mathematically impossible results when it's forced into the quantum realm.
Completely intractable.
Yeah. But what's novel about Julio Chai's paper isn't the problem itself. It's his highly specific mathematical patch.
Right.
Okay, let's unpack this, because to really grasp the mechanics of Chai's hyperexponential patch, we have to look at the architecture of that first map.
Einstein's general relativity.
Exactly. And for anyone who follows physics, we're talking about the Einstein field equations. Specifically, this relationship where the geometry of spacetime, which is represented by the g mu nu tensor, is dictated by the energy and momentum within it.
Which is the t mu nu tensor.
Right.
Yes, the equation is a g mu nu equals 8 pi g over c to the 4th times t mu nu.
It's just so famous.
It is arguably the most elegant equation in human history. To kind of translate the architecture of that math for you, the left side, the g mu nu tensor, is a purely geometric construct.
Yeah.
It describes a smooth, continuous manifold. It essentially tells us how space-time curves and bends.
Like the classic heavy sphere on an elastic fabric metaphor.
Exactly. And the right side, the t mu nu tensor, the stress energy tensor catalogs all the mass, energy, and pressure in that region.
So matter tells space-time how to curve.
And space-time tells matter how to move.
But the underlying assumption of that left side, the geometry side, is that it is completely continuous, right?
Yes.
Like you can zoom in forever, and the fabric of space-time remains smooth and predictable. It's totally deterministic.
Exactly. It relies on Riemannian geometry, which basically assumes no gaps, no jumps, no underlying granularity at all.
It's just one seamless sheet.
Right. If you calculate the orbit of a planet or the path of light bending around a distant galaxy, the math just flows seamlessly.
Which brings us to map number 2.
Ah, yes.
Quantum mechanics, where the entire concept of a seamless flow just completely goes to die.
It really does.
Because in the quantum realm, nothing is continuous. Thanks to Max Planck, we know that energy, momentum, and even light itself are divided into these discrete, indivisible packets called quanta.
And that introduces an absolute philosophical and mathematical nightmare when you try to merge the two theories.
I can imagine.
Because quantum mechanics isn't just discrete. It's also probabilistic. A particle doesn't have a single definite location.
Right. It's just a wave of probabilities until you look at it.
Exactly. It exists as a smear of probabilities, a wave function, until it's actually measured.
If we were to use like a musical analogy for this,
Oh, I like those.
general relativity is a classical orchestra playing these smooth, continuous, sweeping chords. The violins glide effortlessly from one note to the next without any breaks.
It's a continuous wave of sound.
Right. But quantum mechanics is digital electronic music. Everything is broken down into quantized, discrete beats built on these highly specific, microscopic pixels of sound.
Oh, that's a great way to put it.
There is no smooth glide between the notes.
Oh,
It's just on or off. Step one, step two.
What's fascinating here is that we aren't just dealing with two competing hypotheses where one of them must be wrong.
Right, because they both worked.
They do. Both maps are undeniably real and empirically proven. Relativity ensures our GPS networks function with pinpoint accuracy by accounting for time dilation.
Yeah, your phone's map app literally relies on Einstein.
Exactly. And on the flip side, quantum mechanics is the foundational architecture of the microchips in the device you are using to listen to this deep dive right now.
Which is wild to think about.
It is, but mathematically you cannot place a probabilistic, discrete quantum field into a deterministic, continuous geometric tensor.
Because the math literally revolts. It just
And
crashes.
it completely crashes.
And since both maps work perfectly on their own scales, the only way to really test this contradiction is to find an environment where immense cosmic mass and microscopic quantum scale exist at the exact same time.
The absolute extremes of the universe.
Exactly. Which brings us directly to the environments where Julio Chai focuses his correction model. The center of a black hole, or the exact moment of the Big Bang.
Yes. The singularities.
Right.
In standard general relativity, when a supermassive star collapses under its own gravity, it shrinks down into a smaller and smaller volume.
Okay.
And because Einstein's equations assume space-time is infinitely compressible and continuous, the math dictates that the star collapses into a point of zero volume.
Zero volume. And when you divide a massive amount of energy by zero volume, your density just goes to infinity.
Exactly. The curvature of space-time becomes unbounded.
The equations just spit out an infinity.
They do, and in the realm of physics, an infinity is rarely a description of actual physical reality.
Right, it's usually a mistake.
It is a mathematical pathology. It's essentially a flashing red warning light on the dashboard of our theories, indicating that the model has suffered a catastrophic breakdown.
A completely divergent result. But here's where I want to challenge the premise for a second.
Okay, go ahead.
Wait, if Einstein's math breaks down and gives us infinity at the center of a black hole, does that mean Einstein was just flat out wrong about gravity?
Well, if we connect this to the bigger picture, you're touching on the exact reason why thousands of physicists have spent the last 50 years chasing string theory and loop quantum gravity.
Ah.
The instant has absolutely been to rebuild gravity from the ground up as a fully quantum phenomenon, to say, yes, the classical geometric approach is just wrong at that scale.
So why hasn't that worked?
Because gravity fiercely resists being quantized. When physicists try to force the gravitational field into the standard rules of quantum field theory, they encounter these non-renormalizable infinities.
Oh, more infinities.
Exactly. Basically, the math breaks down in a completely different, equally frustrating way.
Man, so we are just stuck. A purely classical approach gives us the singularity. A purely quantum approach gives us mathematical garbage that we can't normalize.
Precisely. And this is where the historical context is really vital.
Okay.
Remember Isaac Newton?
Sure, the apple guy.
Right. His laws of universal gravitation were the absolute gold standard for centuries. They work beautifully for cannons, apples, and the orbits of the planets.
Yeah.
But as we began to observe objects moving close to the speed of light, Newton's equations started to drift from reality. They didn't work anymore.
Right.
But Einstein didn't prove Newton wrong in the everyday sense. He proved Newton was incomplete. Einstein provided a broader framework that simply reduced down to Newton's laws at low speeds.
Oh, I see. So Chai is approaching general relativity the exact same way.
Yes.
He's arguing that Einstein isn't wrong about gravity being geometry. His equations are just like missing a term that only matters at extreme subatomic scales.
Exactly. Chai is proposing a semi-classical patch. He is operating under the assumption that we don't need to throw out the beautiful, proven cathedral of general relativity.
Right. Don't throw the baby out with the bathwater.
Exactly. We just need to recognize where the map ends, and we know exactly where that edge is mathematically.
We do.
We do. It is defined by the Planck length.
Ah, the Planck length.
Yeah.
The absolute threshold of space-time reality as we understand it.
Right.
The source material emphasizes this specific scale, and it is mind-boggling. It's 1.6 times 10 to the negative 35 meters.
It's unfathomably small.
It really is.
Ugh.
It's hard to wrap your head around a number that tiny, so let's visualize it for you listening. Take a single microscopic atom.
Okay.
Now blow that atom up until it spans the entire width of the Milky Way galaxy.
That is a big atom.
Right. If an atom were the size of a galaxy, the Planck length would be roughly the size of a single tree somewhere inside it.
Which is just, wow. It is the absolute fundamental limit of distance.
Yeah.
At this scale, the smooth fabric of spacetime is thought to dissolve into a granular, fluctuating state that we often call quantum foam.
Quantum foam.
Yes. And the core argument of Chai's paper is that spacetime simply cannot be compressed beyond this granular limit.
Okay, so that brings us to the actual mechanics of the Planck-Chai function. How does he mathematically enforce this limit?
Well, he proposes adding what he calls a hyperexponential correction factor to the Einstein field equations.
A hyperexponential correction.
Right, and this is really where Chai's systems engineering background shines. He isn't altering the fundamental relationship between matter and geometry.
Okay, so G mu nu still equals T mu nu, mostly.
Mostly. Instead, he modifies the equation by introducing a multiplier. It's a dynamic regulatory function based on the curvature of spacetime relative to the Planck length.
Here's where it gets really interesting, because an exponential function like e to the x already grows incredibly fast. Right?
Oh, very fast.
But a hyperexponential function scales as an exponential raised to another exponential, like e to the x. Why use something so aggressively powerful for this patch?
Because the divergence at the singularity is violently aggressive.
Oh, right, because it's heading to infinity.
Exactly. Chai needs a mathematical barrier that acts like an impenetrable wall. Let's look at how the function behaves. When you are in normal cosmic conditions, so the gravity of Earth, the orbit of Mars, or even near a standard neutron star, the curvature of spacetime is minuscule compared to the Planck limit.
It's not even close.
Not even close. So in these normal conditions, Chai's hyperexponential factor calculates out to essentially exactly 1.
Ah, and multiplying the stress energy tensor by 1 changes absolutely nothing.
Nothing at all.
The patch stays completely dormant. Einstein's math functions flawlessly, totally untouched.
Right. But when a supermassive star collapses and the density skyrockets, the curvature of space-time becomes tighter and tighter, right? It approaches that microscopic Planck length.
And as it hits that threshold,
As it hits it, the secondary exponent in Chai's function triggers. The factor awakens.
I came up with an analogy for this. Think of this hyperexponential factor like a built-in shock absorber for the universe. Or actually, even better, like a non-Newtonian fluid.
Oh, like cornstarch and water.
Exactly. If you've ever played with cornstarch and water, you know how it works. If you interact with it slowly and gently, which represents normal space-time curvature, it acts just like a liquid.
It just yields perfectly.
Right. It's smooth.
Yeah.
But if you hit it with an immense violent force, like the catastrophic collapse of a dying star hitting a mathematical pothole,
The fluid instantly turns rigid.
yes, it becomes a solid wall to stop the chassis of reality from just snapping.
That is an excellent way to conceptualize the math, really. In Chai's extended equations, as the curvature tries to push past the Planck scale, the mathematical cost of curving spacetime further grows hyperexponentially.
The cost gets too high.
Exactly. The geometric fabric becomes infinitely stiff. It just refuses to yield.
Well, wait, hold on. I have to push back on this mechanically for a second. If the star is collapsing with the force of, like, 10 solar masses, and suddenly spacetime becomes hyperexponentially stiff and refuses to curve, where does all that energy go?
That's the big question.
Right. Doesn't arbitrarily throwing up a mathematical wall violate the conservation of energy?
That is the critical tension in the theory, and it's a brilliant question. Chai's math suggests that the energy doesn't disappear at all. Rather, the dynamic coupling between matter and geometry shifts.
Shifts how?
Well, when the geometric collapse halts, the immense kinetic energy of the collapsing matter can no longer be spent on warping spacetime. So instead, it forces the matter itself to transition.
Transition into what?
This raises an important question, and it's perhaps the most profound implication of the entire paper.
Okay.
If the singularity is mathematically eliminated, if the collapse strictly halts at the Planck scale due to this hyperexponential buffer, what actually lies at the center of a black hole?
Right, if it's not a point of infinite density.
Exactly. The implication is that matter must reorganize itself into completely unknown finite quantum phases.
So instead of an infinitely dense point of nothingness, a black hole actually contains a physical object,
Yeah.
like a hyperdense finite core.
Exactly. Now, physicists have theorized similar concepts before, things like Planck stars or gravistars.
I've heard of those.
Yeah, but Chai is providing a specific, mathematically grounded mechanism for how space-time itself enforces this boundary. We are talking about forms of reality, exotic states of matter, and extreme geometry that our current standard model hasn't even begun to classify.
Wow.
The hyperexponential correction offers a framework where the universe is strictly self-regulating.
It's like finding a hidden physical floor at the absolute bottom of the universe.
That's a great way to visualize it.
And if this holds true for black holes, I mean, it completely rewrites our understanding of the Big Bang too, doesn't it?
Radically, think about it. The standard model suggests the universe exploded outward from an infinitely dense singularity,
Right, from a point of zero volume.
which, again, defies logical physics. It's an infinity. But under the Planck-Chai model, there was a maximum threshold of compression.
The buffer.
Right. The early universe was compressed down to the Planck scale, the hyperexponential buffer triggered, spacetime reached maximum stiffness, and the underlying quantum phase violently rebounded.
A big bounce.
Exactly. A big bounce, governed by a rigid mathematical limit.
Man, that is intense. So what does this all mean?
That's the question we always come back to.
Yeah. Why does a highly theoretical mathematical patch proposed by a Bolivian systems engineer matter to you listening to this right now?
It's a fair question.
I think it matters because the singularity, that mysterious center of a black hole, is the ultimate metaphor for the limits of human knowledge.
It truly is. I mean, for a century, the infinite divergence in Einstein's equations was our horizon. It was the dark edge of the map, a mathematical here be dragons, you know? Many scientists accepted that we simply couldn't ever know what happens inside.
But science is not a static textbook. It is a living, aggressive expedition.
Always pushing forward.
Always. And Julio Chai's hyperexponential correction model is a flashlight pointed directly into that abyss. It reminds us that every anomaly, every broken equation, and every intractable infinity is not a dead end.
No, not at all.
It is simply an engraved invitation from the cosmos to look deeper, to find the hidden variables.
Exactly. It forces us to confront the fact that our classical intuitions, the smooth, sweeping world we interact with daily, are just high-level approximations.
They're just the surface.
Right. The universe is terrifyingly vast, yet undeniably rigidly granular at its foundation. And the fact that human mathematics can build a conceptual bridge between the cosmic symphony of relativity and the quantum whisper of Planck's world, it's just a profound achievement.
It really is. It means the very ground you are walking on right now is upheld by quantum boundaries we are only just beginning to decode.
It's humbling.
Very. Which leaves me with a final lingering thought for you to explore on your own today.
Oh, let's hear it.
So, if space-time itself is truly constructed out of these discrete, tiny building blocks, these Planck lengths, and equations like Chai's prove that they act as a rigid, hyperexponential buffer against infinite compression, does that mean the universe has a maximum resolution?
Oh, wow.
Exactly like a digital photograph or a computer screen.
That is a fascinating concept, a fundamental hard limit to the processing power of reality itself.
Exactly. If there is a hard mathematical limit to how much reality can be squeezed before it simply bounces back, what else in our physical experience is heavily pixelated just beneath our level of perception?
Makes you wonder.
It does. The next time you look up at the night sky, don't just see the smooth, continuous sweep of the stars. Try to conceptualize the invisible, granular pixels of the cosmos, quietly buffering against the infinite.
Beautifully said.
Because out there, in the dark, those two incompatible maps might finally be starting to align.